following schematics, you see where the individual parts are placed on the board. I now will show you the schematics. I came to the conclusion that usually people are really afraid of trying to read schematics because they look completely non-understandable. But if you want to change the code, or for example attach it to your robotas or whatever, or create sniffing devices or create keyloggers with Sputnik, you need to understand the schematics. Therefore, I will give you now a short introduction how to read schematics. It's basically very simple. You just have to believe in yourself. Hang on a second. Okay, the next slide. Sorry. The hardware consists again from a PIC16F684 microprocessor. We mainly chose this microprocessor because it's A, cheap, B, draws virtually no power, and C, you can buy it pre-programmed, and no other manufacturer, to my knowledge, provides such services. You can buy directly from Microchip, so you don't have to pay annoying fees for distributors that are just reselling the devices. So it's on the end cheaper. But I personally also don't like PIC microcontrollers because they are not really high-level language capable. We again use this NRF24L01 2.4 gigahertz front end from Nordic Semiconductors. This is really, really great. You have to read the data sheet. It's readable, and it provides basically all kind of communication functions you need in hardware. So, for example, it provides acknowledging services. It provides a FIFO up to 3 packets. It decodes automatically MAC addresses. It checks CRCs. You can save insane amounts of power by just clocking in the data, turning your processor off, and the NRF chip will handle everything autonomously. You have to be aware that in most cases, the best solution to integrate in your existing design is not by using it with the PIC microcontroller and attaching it to your microcontroller, but by directly using the NRF24L01 HF front end. It's very easy to use. It has a SPI interface. To people that don't know SPI interface yet, it's, in my opinion, the most simple interface to get data into a digital device. You have a clock line, you can clock data in, and you get data out on a this front end. So you definitely have to think about a possibility of only using the NRF processor, and we have a high-level API which is very easy to port to every setting and reading I/O ports, and everything else is done by the API. We again have this battery lithium-ion cell as a power supply. The push button is new, and we provide additional header for attaching piezo buzzers. So this is intentionally left blank. So if some people are interested of adding sound support to Sputnik Tech, we will support them. In my opinion, this even people that are not don't have very much experience with embedded programming can do this task within 1 or 2 days. So this is, I think, a very simple way to pimp your Sputnik tag. Also, there is a second pin, so the program header is not wasted, where you can add additional I/O pin to your own custom hardware. These are the schematics. So the basic idea is that this is the top level sheet. On the top level sheet, you have these green boxes, and these green boxes indicate other sheets that are inside this. So if you want to get an overview, you look at the top sheet, and there you see basically you have two building blocks, a CPU and the RFB. It's a RF front end, and the only lines, the only lines that are used to communicate between those are shown here. So there are no other magic lines except of ground and power. These are global for all sheets. So basically it's a very simple game. It's like in this fast food chains where you have these pictures where you have to follow a line. Here it is even more simpler. The lines are named. So if you have a line, I will zoom. Is this possible? Hang on a second. No. If you have a line, then the line is automatically connected if it shares the same name. So this makes a sheet more reasonable. So if you have a line here that's IRQ, it's automatically connected to another line that is also called IRQ if it's on the same sheet. This ensures that you don't have wide crossings between all kinds of lines, and you lose completely track. So first look at the names for the lines, and then you see where they go. This is the processor. I have a link for the data sheet, and then you know automatically, for example, you want to know how to toggle the clock pin. You follow the line for the clock pin. You see, okay, it's pin 10, and it's RC0. And then you look into the processor manual how to use this. But the normal use for you is, as I said, very simple. You just have to follow lines and look what is connected where. For example, if you want to turn off the or on the LED, you see here's the LED, and you have RC5. You just have to turn RC5 on, and then the LED lights. Or for example, here you have the programming connector, and here you see how the lines are individually connected. Oh, that's also an interesting part. There is also a new change in the tag design. You can choose between two operating modes. For the current use, you obviously want to constantly power the tag, but because it automatically sends data out. But if you move the 0 ohm resistors to this, there is a mode A1 and a mode B1. If you only connect this resistor, then you can turn on the tag with a push button. So for example, if you want to secure your door at home and you want, or your garage, you want to open it with a Sputnik tag, then this will be the most power-saving possibility, because this tag then is only powered while pressing the button. That's the intention. So if you have application where you just want to have action while pressing the button, then you just move the resistor from here to here, remove this resistor, and you have a tag which only acts when pressed, and then the battery will easily last for years. And this is the RF front end. So if you do your own schematics, you just have to add this part and connect this I/O lines to your to free I/O pins. So that's basically all. And you just take the same values and have a look at our layout. And if you want, you can send us our layout, and we will have a look on it if it's done in a proper way, or if you have mistakes, so you don't waste money on PCBs. So if you're interested, just send us your layout, and we can check it. So the current functionality, every tag transmits now 6 to 8 times per second. This is very important because the area is very big. So we want to make sure that even if only every 20th packet is received, that you have tracking with 2 seconds resolution. Therefore, it's much higher than on the Congress, where the tag only transmitted every 1 to 2 seconds. Also, we changed the code that the blinking is not synchronous anymore with the transmitting, because it would cost too much power if we would blink 8 times per second. It only blinks 1 time per second roughly, so don't be confused. It really sends packets out 10 times a second. Then the pseudo-random generator is again seeded with a random seed. It again cycles through 4 power levels, so you can estimate the distance to a reader by checking at which power levels are received how often again. To make sure that if we have areas where the tag density is too high, we want to make sure that there we don't get a denial of service attack. Therefore, we have 2 channels. On one channel, you have a low frequency tag transmitting, and on the other channel, high frequency. So if we get too much sightings on a given area, then we just turn to the second channel, where we have where we get much less beacons per second. Currently, it transmits on channel A 4 times as often as on channel B. Again, the transmission is encrypted by using XXTA block encryption and a 128-bit shared key. We use an incremental sequence number again to make sure that every packet is different, because if only 1 bit swaps in the packet, because of the block encryption, the whole packet changes completely. The shared key is protected by the usual CPU copy protection bits. This is an average security, so you can't take a simple program and read out the keys used. Again, the encrypted packets will be forwarded by our Ethernet readers in the shelters and sent to aggregator, where they will be stored after decryption. And because of the encryption, the data gathering can be only done by the owner of the tracking system, which obviously knows the shared key. So sniffing, so it's I think a pretty good protection. How to write your own code for Sputnik? The entrance fee is pretty nice. Basically, you only need a PicKit2 programmer. This is a pretty convenient device. You have it's USB. It has a USB interface, and so you can work on your laptop easily, and you can reprogram the devices easily with the Sputnik tags with this programmer. We used the first for the current software using this high-tech PICC Lite compiler, but it turned out that only few people participated because you had to use the Lite version of the compiler, which only supports half of the flash. So we had to throw out the encryption for the Lite version, so everyone is able to build firmware images. So what we also will do in the next weeks is to port the firmware to SDCC. I personally hope that, because it's usually it's a very simple job to port this into a different compiler. This PIC 16684 is perfectly supported in SDCC, and I hope someone will take a day and port it, but no one turned up and ported it, so we had to port it by ourselves. So if you're interested in porting it here on the Congress, we will support you as much as we can. You can sit at our booth, and so you have a direct connection to us, and we will assist you in porting it to SDCC, so more people can use the real compiler and reprogram the tags to their own use. This PICC compiler really sucks. You don't really want to work with it. Basically, you need average C compiler skills. I think the code is pretty readable, and you need, obviously, time. Porting, as already indicated, is pretty simple. You only have to replace some atomic functions and which deal with setting and reading pins. I think this is